sky never lied and brought me to the dark. One by one into the fire.
Galaxies, massive celestial conglomerations consisting of countless stars, planets, and nebulae of gas and dust. Radiant worlds, dominated and held together by dark matter. Only with their discovery did the universe, as we understand it, grow to the dimensions we know today. And their observation gives researchers clues about the traces of our origins.
What do we mean by galaxies? Well, the stars in our universe are not evenly distributed. Under the influence of each other's gravity, they clump together to form a galaxy. Typically, 100 billion stars form a galaxy. Our galaxy is called the Milky Way. What happens to a young galaxy? Well, it rotates, and you could say that the stars are hurled onto the plane of rotation, which is stable. But the stars in this disk are not evenly distributed either. Spiral arms form over billions of years. In other words, old galaxies can be recognized by their spiral arms, while young galaxies are beautifully spherical.
Spiral galaxy M74, also known as phantom galaxy. This image shows a combination of data from two space telescopes, Hubble and James Webb. A fascinating photograph that extends from the infrared to the ultraviolet range. Huge structures of dust and gas are shown in red, while star-forming regions spread across the entire galaxy are lit up in pink. Galaxies are gigantic celestial systems, groups of billions of stars bound together by gravitation, surrounded by planets, gas, and dust. With modern telescopes, researchers peer deeper and deeper into the universe, almost all the way back to the Big Bang. Thus, they look into the stellar nurseries of distant galaxies.
There are more galaxies than we had assumed, also based on our cosmological simulations. And the galaxies evolved faster during this early time than we had thought in theory. This rebuttal of most previous models is thrilling to scientists.
The Milky Band in the night sky was a mystery for a long time. At the beginning of the 17th century, Galileo discovered that it consists of countless stars. In the mid-19th century, astronomer Thomas Wright imagined our galaxy as a spherical structure alongside countless others. Wright's realization that our Milky Way was a galaxy was taken up by Immanuel Kant, who in 1755 interpreted the visible nebulae as other galaxies, so-called world islands. However, this went unnoticed. Kant was a philosopher and not an astronomer. In 1786, William Herschel finally compiled a catalog of nebulous objects that he identified in the night sky. In fact, they were distant galaxies. Today, researchers are still looking deeper and deeper into space, striving for knowledge and understanding.
It's about gaining insights about the universe, not to exploit them economically, but simply out of curiosity. Curiosity is an incredibly strong drive for us humans. And it's particularly fascinating that in astronomy, we can pursue the human urge to answer deep questions about the cosmos, about our own origins, and about our place in the cosmos.
For a long time, researchers were unable to decipher the nature of the nebulous patches of light in the night sky. The resolution of their instruments was too low. However, scientists already suspected that there could be other star systems besides the Milky Way. At the beginning of the 20th century, the astronomer Edwin Hubble pointed a powerful telescope at the mysterious structures. By determining their speed and distance, he wanted to bring order to the seeming chaos in the night sky. Hubble realized that some of the nebulae were comprised of countless stars. Suddenly, we were no longer alone in space. Scientists recognized that our Milky Way was just one of many groups of stars. Thus, once and for all, Hubble put an end to the so-called Great Debate about the nature of nebulae and galaxies.
So what does our Milky Way actually look like? The answer is exactly as shown in this diagram. We have a thick bar in the center, from the ends of which two huge spirals start. And if you wonder where our sun is, the answer is here, on a small branch, the so-called Orion arm. Is it a coincidence that we live there? No, it's not. Because if we lived further in, somewhere here on this bar, we wouldn't survive long because many supernova explosions occur there. On the other hand, the stars further out have hardly any planets, so no place where life can develop. Our location in the Milky Way is perfect for life to emerge and to survive.
Our Milky Way is around 13.6 billion years old, making it one of the oldest galaxies. Its center of mass, the so-called barycenter, lies around 27,000 light-years away from us. Our Sun, and with it the Earth, orbits it at a speed of up to 960,000 kilometers per hour. One orbit takes just under 230 million years, or 1 galactic year. On this time scale, our Sun is only 20 galactic years old. The oceans and the first life emerged 17 galactic years ago. It then took another 10 galactic years for multicellular organisms to form. We live in a spiral galaxy, but we will never see it from the outside.
The Milky Way we see in the night sky is actually the view into the disk. We're rather close to the edge, and the bright band is actually the plane of the disk in which our Sun is located. We're moving in a circular orbit around the galactic center. At the age of the dinosaurs 150 million years ago, we were on the other side of the Milky Way. We're circling around the center together with our local neighborhood.
Astronomers categorize the Milky Way as part of the so-called local group. By cosmic standards, this is a rather small cluster of galaxies, with a diameter of around 5 to 8 million light-years. Within this local group, the Milky Way is the largest galaxy. The second largest is the Andromeda Galaxy, 2.5 million light-years away, our next-door neighbor.
At the same time, there are smaller galaxies that are 100 times lighter, like the Magellanic Clouds or the Triangulum Galaxy, and we've seen even smaller galaxies, 1,000 times smaller than the Magellanic Clouds.
The Milky Way is one of the oldest galaxies in the universe. Scientists estimate that the first stars in our galaxy formed 200 million years after the Big Bang. Around the center, researchers have identified 2 million stars from this early period of the galaxy. Because of their low metal content, astronomers call the area the poor old heart of our galaxy.
The Milky Way was not as big as it is today right from the beginning. It was a much smaller structure. The first stars that formed now can be found in what we call this thick disk. And then there are other structures, the whole expansion that we can see today. Clearly, galaxies have a wide past, and you can see that in the local group too.
Part of our galaxy stretches across the night sky like a milky brush stroke. This is where its name, coined in ancient times, comes from, the Milky Way. The dark patches are interstellar clouds of gas and dust. When we look at the Milky Way in winter, we look at its dimly lit edge. In summer, we look towards the center of the Milky Way, which looks like a bright spot. The Earth's axial tilt allows us to observe different regions of the Milky Way.
If you take the line spectrum from a hydrogen atom, you can practically look through the entire galaxy. And because it's line radiation, you can also see how the gas is moving. The Doppler shift allows you to see whether the gas is moving towards you or away from you. It's like when the police drive past you with their siren on. At first you hear a high-pitched sound, and as they pass by, the sound gets lower and lower. You can deduce where the gas is in a similar way. You also know how big the galaxy is and that it has spiral arms. So from all the wavelengths, you create a picture of what our galaxy looks like.
With the European Gaia mission, researchers seek to discover more about the formation, development, and composition of our galaxy. The probe is surveying a part of our Milky Way. Gaia will precisely measure and map the position of around 2 billion stars and thousands of extrasolar planets. In the process, the probe will create a precise three-dimensional map of an area in our galaxy. In addition, Gaia is certain to discover and catalog a vast number of other celestial objects, like the remains of stars, stellar explosions, so-called supernovae, and several 100,000 distant galaxies. Gaia is also identifying the position of more than 150,000 asteroids in our solar system. The European mission is collecting a huge treasure trove of data.
In essence, Gaia is surveying the Milky Way. We are determining the position and speed of every star, or almost every star. In other words, classic astronomy. And you might ask, what can I actually do with this information? For example, Gaia has discovered that there are streams of stars that originate from our neighboring galaxies in the halo of our Milky Way system. We can see how our galaxy was formed by doing archaeology in our Milky Way system. So there are exciting things to come.
Another European scout in space is Euclid. The telescope is on its way to explore a yet unknown part of the universe. Space consists of 95% dark matter and dark energy. Euclid will systematically investigate the influence of these mysterious forces on the development and structure of the universe. While dark matter dominates the gravitational effects inside and between galaxies, dark energy is responsible for the accelerated expansion of the universe. Even the first test images from Euclid confirm the telescope's capabilities. What looks like an almost infinite collection of large and small points of light, upon closer inspection turns out to be a crystal clear image of thousands of galaxies. Euclid has two cameras. One takes high-resolution images in visible light, while the second instrument measures near-infrared light and delivers both images and spectra.
Euclid's job is to precisely measure space by observing billions of galaxies and to make observations of the weak gravitational lensing effect in order to examine how the expansion rate of the universe has changed over time. In other words, we want to reconstruct the expansion of the universe. And if this is successful, then we can decide whether dark energy really is a cosmological constant or a dynamic field. It's one unsolved problem of modern physics as to what dark energy really is.
Dark energy is causing researchers headaches. Some suspect that it is the driving force behind the accelerated expansion of our universe. However, the supermassive black holes in the center of galaxies could also play a part in the expansion. A controversial theory.
The black hole at the center of our Milky Way contains an incredible 4.2 million solar masses. We call this a supermassive black hole. And we now know that there is a supermassive black hole in every major galaxy. The largest that we know of in the center of a galaxy is M37. It has around 6.5 billion solar masses. But why is it that supermassive black holes form in the center of a galaxy? Because the stellar density is the highest there. Every larger star ends up as a small black hole. And the density of these stellar corpses is highest in the center of a galaxy. This is where they meet and gradually form a massive black hole until it becomes the one black hole at the center of each galaxy.
Sagittarius A star is the supermassive black hole in the center of our Milky Way. It is the most compact form of matter that science can imagine. The gravity there is so massive that even light cannot escape from its innermost region. That's why you can't see black holes. However, they do exert a visible influence on their surroundings. And researchers can observe and analyze this influence. The area around the black hole in the center of our galaxy is called Sagittarius A. For scientists, this is one of the most exciting places in our Milky Way.
The first indications that there's a very large mass and a very small area in the center came from observing movements of gas. Then measurements made it clear that it could only be a black hole. We measured the orbits of individual stars around the black hole. Based on their movement, we can tell how heavy the mass in the center is. It's like saying our Earth is moving around our Sun at a certain speed, and that's how we know how heavy our Sun is.
The 27,000-year distance to the center of our Milky Way seems small when thought of in cosmic dimensions. However, it enables us to observe the region in detail. In 2022, the black hole at the center of our galaxy was captured in an image for the first time. This picture shows the so-called Shadow of Sagittarius A star, surrounded by a ring of hot matter. The immediate neighborhood of the black hole is characterized by its enormous gravitational force. It causes the stars there to move faster than all other stars in our galaxy. For a long time, researchers had assumed that no new stars could form there. But now they have found a young stellar object, a massive star that has been named X3A.
You can see a kind of baby star there. The star is still in a very early phase, only 10,000 years old, which is actually very young. And it has about 15 times the mass of our Sun. So, in that respect, it's already a rather massive star. This is exciting as you wouldn't expect a gas cloud to be able to hold up under gravity and then collapse this close to a black hole. So, this is very unexpected.
In the center of our galaxy, just a few light years away from the black hole, there is a region that apparently does fulfill the conditions for star formation. The researchers identify X3A as a young stellar object in its formation phase.
In this region around the black hole of our Milky Way, you wouldn't expect many stars to be able to form, simply because the magnetic field is so strong. It supports clouds against the force of gravity. Surprisingly, this theory is now being called into question by observations. Not only did we see gas clouds in the galactic center, a very young, extremely massive star has also been discovered in one of them. It was rather unexpected that our idea of star formation in the galactic center would be put to the test. It shows once again that our theories of star formation are not yet complete.
Another phenomenon was observed near the galaxy RCP-28, 7.5 billion light-years away. A black hole that appears to have been ejected from its galaxy now has a long ribbon of stars trailing behind it, an effect that can arise from a disturbance of the equilibrium. For example, when a single black hole comes too close to two coupled black holes. Our Milky Way will also change. In 3 to 4 billion years, it will meet our neighbor, the Andromeda Galaxy, and merge with it over the course of another 3 billion years. However, you shouldn't imagine that individual stars collide with each other. The stars are extremely far apart compared to their size. During such a merger, it is mainly the gases, dust, and dark matter of the galaxies that interact with each other. New stars can then form from the condensed material. The stars already in the galaxies pass by each other without colliding. A collision between two stars is therefore very unlikely. The merging of galaxies is also a process that takes place over an enormously long period of time.
How do galaxies form? After the Big Bang, there was practically only hydrogen and dark matter, which is often forgotten about because you can't see it. And both clumped together over millions and billions of years to form galaxies. The regular matter followed the dark matter because it's 5 times more common. And now, let's imagine a large cluster at the beginning that rotates very slowly and then collapses. The pirouette effect will cause such a galaxy to rotate faster and faster until the centrifugal force counterbalances the gravitational force. And that's the state we're in, which is why practically all galaxies are in equilibrium today.
Although as early as the middle of the 18th century, Immanuel Kant correctly interpreted the nebulae visible in our night sky as distant galaxies, many astronomers, until the beginning of the 20th century, still held the view that our Milky Way was unique and that there was nothing beyond it except empty space, a lonely island of stars. Then, in 1924, based on his measurements of the distance and speed of objects in the night sky, astronomer Edwin Hubble identified the Andromeda Nebula as a system outside our Milky Way, an independent galaxy. The Andromeda Galaxy is a spiral galaxy, 2.5 million light-years away from us. Its diameter is about twice as large as our Milky Way, and it is home to more than 10 smaller dwarf galaxies. A supermassive black hole also rotates in its center. Researchers have also discovered a number of neutron stars and several smaller black holes there. Hubble also provided evidence of irregularity in the movement of celestial objects, pointing to the general expansion of our universe.
Around 100 years ago, in the 1920s, he was the first to recognize that the nebulae, as they were called in astronomy at the time, were not nebulae, but in fact distant galaxies. He first proved this for the Andromeda Galaxy and for the Triangle Galaxy by measuring the distance to certain stars in these galaxies, Cepheid stars. And this enabled him to demonstrate that they are too far away. These Cepheids in the Andromeda Nebula must belong to a different galaxy.
Scientists are using models to try to find out how the large structures, galaxies, and stars that can be observed today were able to form directly after the Big Bang. The so-called Millennium Simulation, an international research project, and the Aquarius project, which grew out of it, are looking at billions of celestial objects. This is based on dark matter, which, according to the current standard cosmological model, makes up the majority of material matter in the universe. Without the gravitational force of this dark matter, the clumping into galaxies would take much longer, and our universe would look completely different.
We can depict dark matter on the computer and give it color. These are artificial images that are fascinating. But in reality, we only ever see the luminous structures of the galaxies in space, and they're located at the intersections of paths of filamentary matter. That's where the shining stars are. And like lighthouses, they mark parts of the cosmic web.
With the help of today's supercomputers, researchers are trying to recreate how the cosmic structure was formed. The particles that must make up dark matter have not yet been detected. But there is a whole range of indirect evidence in the universe that dark matter must exist.
For the galaxies to form, there had to be a material that had a gravitational effect to bring the galaxies together. We call this material dark matter because it doesn't emit light in the conventional sense. And the question is, what is dark matter? As astronomers, we can only characterize it by gravity. That's the only thing we can measure, and the only way we can see it. But as physicists, we would like to know, is it a special type of particle that we haven't identified yet? We have been able to rule out many things. One idea was that it could be heavy neutrinos. We were able to rule that out. Another idea was that it might be objects that we can't see, like extinct stars, white dwarfs, for example. We can also rule that out. In other words, we have ruled out many things, but we still don't know what is it about dark matter that enables galaxies to form in the first place.
Matter is distributed very differently in today's universe than in the past. It is more clumped together today. Researchers use simulations to reconstruct the formation of our galaxies, their various shapes, and their distribution in space. With the ever-increasing performance of computers, simulations are also becoming increasingly refined.
The difference between the Millennium Simulation, a major project carried out more than 15 years ago, and our best simulations today, Illustris TNG, as we've called them, is that we can now simulate gas dynamics, for example. We can also simulate magnetic fields. This wasn't possible in the past because we didn't have enough computing power or sufficient storage capacity. Today, we can now increase the physical accuracy of this simulation with more modern computers.
Researchers see a delicately spun web of matter, strands called filaments that intersect at certain points. Clusters of galaxies are then found at these crossing points with particularly large amounts of matter. These, in turn, join together at the intersections of the cosmic web to form so-called superclusters. Our Milky Way also belongs to such a supercluster, which researchers call Laniakea, after a Hawaiian deity. This structure contains many thousands of other galaxies in addition to the Milky Way. But even Laniakea is only part of something much bigger.
At the large crossing points of the large filaments, you have these large galaxy clusters. And at particularly thick filaments, there are several galaxy clusters close together. This is called a supercluster. The largest thick filament that's been discovered so far is the Sloan Great Wall. This structure contains more than 10,000 galaxies.
This giant wall is a thread of galaxy clusters stretching through the universe, over 1 billion light-years long. The Sloan Great Wall is part of the filaments of the cosmos. The dimensions are beyond imagination and are not compatible with human experience. In their simulations, however, researchers make these dimensions tangible. Scientists call the largest cosmic superstructure known to date Hercules Corona Borealis Great Wall, a filament with a length of around 10 billion light-years.
At the beginning of the last century, the astronomer Edwin Hubble was one of the first to look at the precise movement of galaxies. He found that hundreds or even thousands of galaxies gather and move around each other, forming a galaxy cluster. And if you put several galaxy clusters together, so-called superclusters are formed. Together with galaxy clusters, superclusters form the largest structures in our universe, the Great Walls. However, when he looked at the structure of the individual galaxies, he realized that they are quite different from one another, depending on the size of a galaxy and its age. And from this realization, he developed a classification scheme for galaxies that is still used today.
With his Hubble sequence, the astronomer brought order to the galactic zoo he had discovered. He drew up a diagram according to which 3 classes of galaxies are still roughly differentiated today: elliptical galaxies, spiral galaxies, and barred spiral galaxies. There are also so-called irregular galaxies, which have neither clear structures nor symmetries. Within this rough categorization, there are a whole range of other types that do not fit into the classic scheme. Spiral galaxies have plenty of gas and dust in their arms, the areas that produce young stars. In the center, there is always a bright spherical core, the so-called bulge, a concentrated accumulation of mass. Compared to such striking spiral galaxies, elliptically shaped galaxies differ significantly except for the bulge. Elliptical galaxies appear rather featureless.
The stellar orbits are scattered. There's a jumble of stellar orbits. An elliptical galaxy usually comes about when a disk galaxy is disrupted, for example, when it merges with another galaxy. Then elliptical galaxies are formed, and those can also merge with each other. And then you get even larger elliptical galaxies.
One of the largest known elliptical galaxies is IC 1101. This huge object has a diameter of around 4 million light-years and is home to many trillions of stars. With the help of astronomical simulations, such as the ongoing International Illustris project, scientists are researching the formation of galaxies. These simulations are generated by supercomputers, many thousands of computers connected in parallel, which together utilize several 100,000 computer cores. The calculations enable researchers to confirm cosmic development and their theoretical models. For example, they track the merging of disk galaxies into giant elliptical galaxies.
Die elliptischen Galaxien sind eher so kartoffelförmig.
You could say that elliptical galaxies are potato-shaped. Their stars are on random orbits. It's a knot of stellar orbits, quite different from the disk galaxies, which has ordered circular orbits. So we have these two completely different galaxy structures. And we actually believe that the basic form that a new galaxy has is in fact the disk form.
Perhaps one of the best-known galaxy motifs is Stephan's quintet. 4 closely spaced galaxies with a fifth in the foreground. The group was discovered in 1877 by the French astronomer Édouard Jean-Marie Stephan. The 4 galaxies are in a kind of cosmic dance and clearly influence each other through their gravitational forces. Our Milky Way also has 2 companions, the large and small Magellanic Clouds, 2 dwarf galaxies that probably only joined the Milky Way a few hundred million years ago. They are visible in the night sky of the southern hemisphere as 2 blurred, cloud-like objects. They're classified as irregular galaxies.
There's no clear structure in the distribution of stars. And this is mainly because most irregular galaxies are smaller galaxies, lower in mass than our Milky Way, by a factor of 10 or less. They don't have a lot of old stars that you could see, as is the case with elliptical galaxies. But some have star formation, so there are young stars shining very brightly, and therefore the structure appears irregular. Typically, these galaxies also have a much higher proportion of gas than of stars. And the distribution of gas is not as well organized as in spiral galaxies, causing these galaxies to appear irregular.
Galaxies are classified solely according to their shape. However, statistical analyses of the shape and color of galaxies tell astronomers more about their properties. From the spectra of a galaxy, researchers can determine how many young and old, high-mass and low-mass stars a galaxy contains. Irregular galaxies often shine very brightly. This is an indication of a large number of stars. And the rounder the shape of a galaxy, the older the stars in it, according to the scientists' hypotheses. For researchers, this confirms that the massive star systems in the early cosmic period were formed primarily through mergers and collisions.
It was only recognized decades later that many irregular galaxies are the result of galaxy crashes, or like the Magellanic Clouds, satellite systems that have fallen into the Milky Way.
Satellitensysteme sind, die in die Milchstraße hineingefallen sind.
This is also known as galactic cannibalism. They absorb smaller galaxies.
Bevor die aber vollständig aufgelöst werden.
But before those are completely absorbed and their stars get in line with the stars of the absorbing galaxy, the incoming galaxy is bullied and disturbed by gravitational forces.
Gepiesackt und gestört und an ihr wird gezerrt.
They tug at it, grinding down their outer areas. And this is how irregular galaxies are created that no longer fit into the usual scheme.
Extraordinary galaxies are given extraordinary names. NGC 2442, for example, was given the nickname Meathook. Astronomers call the galaxy M51 the Whirlpool Galaxy, a fascinating beauty that was captured in drawings in 1850 by the Irish astronomer William Parson as a spiral nebula. With its distinctive arms, the spiral galaxy is one of the most recognizable objects in the night sky. It has approximately the same size and luminosity as our Milky Way. The so-called wagon wheel galaxy is surrounded by a ring of bright newborn stars. It probably owes its unusual shape to a frontal collision with a smaller galaxy. All these celestial objects are the visible building blocks of the cosmic architecture.
Galaxies and galaxy clusters form thread-like structures, so-called filaments. Where the filaments come together, nodes are formed, and superclusters are created. Sometimes even surface-like structures, like the Great Walls. All of this combined makes up the structure of our universe, the cosmic web. However, this web is subject to constant gravitational change.
The young universe is primarily dominated by dark matter. Its gravity determines its structure, and thus shapes the distribution of galaxies, gas and dust nebulae. But the universe is not static. Nothing stays the same. And so galaxies also change over the course of time. They form, evolve, and merge with each other, and in this way form new celestial objects. The first galaxies were formed 200 million years after the Big Bang. Before that, our universe was pitch black, a time that astronomers call the Dark Ages. There were no stars or other sources of light, but tiny fluctuations in density began to form large-scale structures during this time.
Also irgendwann ist der erste Stern entstanden und
at some point, the first star was formed, and with the appearance of the first stars, the Dark Ages ended. And this period was not particularly long in absolute time. It can be researched, but it's exceedingly difficult. There's only one direct source of information, the 21-centimeter hydrogen line. At some point in the future, we'll be able to use it to observe the Dark Ages. At least, we can research them. This 21-centimeter hydrogen line could be used to investigate the density fluctuations that existed at that time. In the Dark Ages, the universe was a uniform soup of matter and radiation, to put it casually. But there were some slight fluctuations in density from which the first galaxies later emerged.
Gravity is the driving force behind the cosmic web. It has an infinite range and cannot be shielded by anything. As a result, places of larger accumulations of matter always attract new material, a self-reinforcing process that can only be counteracted by expansion, the rapid expansion of the universe. But the expansion does not change the increasing clumping of the local filaments. The filaments thin out. Huge cavities grow between the accumulations of matter, so-called voids.
The cosmic web is no longer becoming stronger. On the contrary, it's now thinning out. Parts of the thinner filaments are becoming thinner and will eventually tear. In the distant future, we'll no longer be able to observe many areas that we can still see today due to the ever-increasing acceleration of space expansion.
The structure of this cosmic network has been systematically recorded since the 1980s. One of the most ambitious projects is the Sloan Digital Sky Survey, a long-term series of sky surveys running in several phases. With this program, researchers have recorded more than 4 million galaxies and quasars, the highly luminous active centers of galaxies. They use the data to create a three-dimensional map showing the spatial distribution of galaxies in large parts of the cosmic space surrounding us. The project has led astronomy into the era of large data collections and archives, a glimpse into the eventful past of our universe. The future, on the other hand, promises to be a rather quiet time.
In a way, the universe is becoming more boring. Why do I say that? Well, stars have an origin. If you look at where most of the stars were formed, that was at a redshift of about 3. So not that long ago if you compare it with 12. This is how we measure things. But nowadays, star formation happens less and less. This means that much more gas is converted into stars, and at some point, star formation will probably come to a standstill. Only star corpses will be left. No more planetary systems will form, and light will disappear from the universe. And it will become a pretty boring place.
Researchers now assume that our universe will continue to expand for all eternity. This theory is based on the observation that galaxies are moving away from each other at increasing speed, driven by a mysterious force, dark energy. While its true nature is still completely unclear, the effects of dark energy on the universe are observable to scientists. There appear to be no temporal or spatial limits to the expanding cosmos. Matter will continue to clump together, and in an infinitely expanding universe, only a few lonely, huge clusters of galaxies will remain.
The universe is already past its prime. It's simply the case that activity in terms of the formation of new galaxies has greatly diminished. This has been the case since the heyday around 5 to 6 billion years ago. We're talking about a freeze-out of cosmic structure formation. And interestingly, this is due to dark energy. This is because the universe has started to expand faster and faster, and this has given gravity an immensely powerful opponent. The existing structures only grow a little bit more, and then it's the end of the road, so to speak.
The freeze-out as the end of all existence. Our cosmic world began in the Big Bang 13.8 billion years ago. Until recently, cosmologists assumed that the end of the universe would be a kind of reversal of its beginning. The idea was that the force of gravity would slow down and eventually reverse the expansion of the universe. Just like a stone thrown into the air, falling back to the Earth. But then, thanks to precise measurements of supernova explosions, researchers realized that the expansion of space was increasingly accelerating. So there had to be another unknown type of energy, a dark energy that dominates the universe and determines its end.
It's well known that a hole is where something is not. And the same is true for matter in the universe. Over time, the matter clusters into filaments and leaves behind empty space, holes, the so-called voids. Both filaments and voids together characterize the increasing compression of the structure of our universe. And what does compression mean? Well, the galaxies are coming closer and closer together, and with them, the dark matter that we cannot see. And they merge over long periods of time. An example? Our Milky Way will start merging with the neighboring Andromeda Galaxy in around 3 to 4 billion years. Then the whole process will take about another 3 billion years. So after about 7 billion years, there will be just one galaxy. Luckily, that doesn't need to bother us at all, because our sun will only exist for another 5 billion years anyway.
Galaxies. Shining islands in the ocean of the universe. They are not just a collection of stars, planets, and clouds of dust and gas. They are the chroniclers that record the evolution of our cosmos. Galaxies are the witnesses that reveal the history of the universe to astronomers, in a fascinating tale of development and change. Islands of worlds where stars extinguish and new ones are born. Their past and their future are determined by the competition between gravity and dark energy. And in the distant future, the galaxies themselves will be lost in the darkness of ever-expanding space.